Hello everybody, I'm here to talk about the trace contamination experiment. It's going to be named experiment 1, but some of you are doing it the first week and some of you are going to do it in the second week. So you definitely want to watch this video before that, and you also want to read through the procedure. So if we take a look at the procedure here, you'll see that there are some links embedded in the procedure. So you want to click on them because most of them are either something to read or a video that will help you learn how to do a specific task that you're going to need for the lab. It's important when you watch videos that you are like actively taking notes, making drawings, making kind of like a guidebook for you to use, because of course you're not going to have the video when you get to the lab. So this, for example, teaches you how to use a graduated cylinder, which is one of the first things that you're going to measure with in this experiment. Okay, and so this is a pretty simple experiment to do, but it actually has 4 or 5 hypotheses embedded in it. And so what you're going to do initially is clean a bunch of beakers, 8 of them. And then they need to be dried in the oven. And what we're going to have to do is your instructor or the technician is going to allow you to do that one at a time. Don't just wander around the lab. Wait until you're able to do that, and the instructor will come and tell you. They've got to be in the oven for about 20 minutes. So in the meantime, you're going to do one of our other hypotheses, which has nothing to do with the beakers really, because as it turns out, beakers are really, really inaccurate. Oh, actually, imprecise as well. So I happen to have one here at home. Let me show you this. So this is just water with some food dye in it, but once my camera cooperates, maybe we'll see the lines. So beakers have markings about every 50 milliliters or so, which is not a very precise measurement, right? Okay, camera's not going to cooperate. So anyways, you can see that this beaker has very few lines on it, and that means that you're not going to get a very precise reading from it, which means not very many significant figures. Every beaker is also equipped with a tolerance on it, and this one says, I don't know if you can read it, but it says plus or minus 5% right there. That means that if I have filled it to the 200 milliliter line, it could be anywhere between, so the actual volume could be anywhere between like 237 milliliters and like 262 milliliters. You get like a 30 milliliter range. That's a lot, right? And so we don't use beakers to actually measure amounts of anything. Instead, you're going to use a graduated cylinder to do your measuring of your initial volume. And we need 200 milliliters, so this is a unique opportunity to compare 2 different graduated cylinders that are going to be left out for you to use. They're already cleaned and ready to go. So what you're going to do is weigh them on the balance, and there's a video for how to use that, so make sure you've watched that. You'll have a balance at your desk, so you're gonna weigh it on the balance, and you got to keep track of which one is which. I would mark them with a grease pencil, maybe graduated cylinder 1 and graduated cylinder 2. But weigh them, and then you're going to fill each of them with 100.0 milliliters of iron 3 chloride, which is conveniently called orange stuff or brown stuff because that's kind of what it looks like. If the graduated cylinders didn't have any uncertainty, they would measure exactly the same mass if you fill them both up to a 100 milliliter line. That's not going to be the case. It's virtually impossible, except for by luck, to actually get the same exact mass using 2 different devices. And in fact, if we had more time in the experiment, you could measure that same volume several times with the same graduated cylinder, and you would actually get different amounts. Okay, this is called uncertainty, and it's unavoidable. Every single measurement ever taken has uncertainty, no matter how careful we are. And so in this introduction that you're going to write for this experiment, you're going to talk about uncertainty, and you're going to want to do a little bit of research and figure out what types of uncertainty might apply in a chemical experiment. So uncertainty is a precision measurement that you're going to use, and we can do statistical calculations to see how much uncertainty any given measurement might have. And of course, the lower that number, the more reliable the data is. Okay, so that's what you're going to do for the graduated cylinder comparison. You're going to explore uncertainty between the two cylinders. And actually graduated cylinders, 100 mil graduated cylinders, actually have 4 significant figures of data. So that's actually pretty good. We would expect the uncertainty to be pretty low. If you did this experiment with this little beaker, the uncertainty would be really high. Plus or minus 5% is a big range, right? So the mass of the water inside of that flask is going to differ extensively from another beaker. I said flask, I meant beaker. Okay, so that's one experiment. By the time you're done measuring your masses, your beakers are probably going to be dry. Once again, let your teacher know that you're ready to go pick them up, and they will tell you when you can go over to the oven and get the things out of it. Try not to take anyone else's beakers. That's why you label them before you put them in the oven. So the next part of the experiment is going to use those 100 milliliter graduated cylinders to get about 200 milliliters of orange stuff. I didn't have orange food dye, I had pink. So I'm using this to simulate that. So what you're going to do for this part of the experiment, after you have gathered your empty weight for your graduated cylinders and your full weight for your graduated cylinders, the next thing to measure is whatever beaker you have labeled as beaker number 8. Make sure it cools off, because it'll mess up the metal on the scale, so let it cool. Then get your mass for beaker number 8 before you start the transfer loss part of the experiment. Okay, so the next hypothesis is that every time you transfer something from a container, you lose a little bit of it. And I thought about this today when I was making my daughter lunch. So this is our peanut butter jar, and she was desperate for peanut butter and jelly and peanut butter with apples. And I don't know if you can see this all that well, but there's still some peanut butter in here, but I can't get it out. Because as everybody knows, peanut butter is super, super sticky, right? That means it has high intermolecular forces. We're going to learn about those things at the end of the semester, but essentially they like to stick to each other on a molecular level, so they're also sticking pretty strongly to the container. This is transfer loss, right? However much material is left in the container is no longer useful for the next part of my experiment, feeding my kids, right? So that's going to happen for everything you transfer. If you've ever tried to make cookies and you don't have a big enough bowl and you got to move it to another bowl, it's always like, oh man, I left a bunch of batter behind. That stinks, right? Or even just when you're making regular cookies, there's always stuff left behind. You can't get everything out, right? And so the next experiment is going to quantify how much of an aqueous solution, in this case iron 3 chloride, do we leave behind every time we transfer. Okay, so what you're going to do is you're going to have your 8 beakers. You're going to pour from your graduated cylinder into the first beaker. And then both cylinders, right? So that's 200 mils. You're going to have about 200 milliliters. Don't use this to measure that. Use the graduated cylinders. And then you're going to pour as carefully as you can. Try to get every bit into the next beaker. Okay, I tried. Okay, and so you're going to keep doing that all the way from beaker 1 to beaker 8. And then you're going to end up with beaker 8 full. I don't know what's up with that camera. You're going to end up with the beaker 8 full of your brown stuff. That is going to be reused, so please just leave it in beaker 8. Set it aside. After you have weighed the mass of that full beaker 8, set it aside so we can reuse it. Don't put anything into that beaker besides the 200 mils or so of the brown stuff, okay? Set that aside. Then what you're going to do with every one of the first beaker is going to be your control. And you can see here, despite the reflections, you can see that there's actually quite a bit of liquid still left in there. I tried to be as careful as I can and pour it all in, and yet still there's some stuff in here. So in order to tell how much of the chemical you're testing is in there, we are going to add potassium cyanide. You're going to make the iron react with cyanide, and that forms a really nice deep blue color. And so it's not going to be pink like this, it's going to be blue. And so you're going to put a couple of drops into the flask, kind of swirl around, and you see the difference. If you put your beaker against something white versus if you don't, it's a lot easier to tell the color, right? So make sure you're using a piece of paper or something underneath your beaker when you're trying to make observations. So beaker 1 is your control beaker. You're not gonna wash it at all. You're just gonna put a few drops of your indicator in there and observe what it looks like with no cleaning. And then in beaker 2, you're gonna rinse it with 10 milliliters of water. So let's draw a schematic of this experiment. This program is pretty cool. It's called Microsoft Whiteboard. It's free, or at least it was for my computer, but it has stickers in it so we can learn about elements. So since this is lab 1, we get to learn about hydrogen, discovered in 1766, and of course it makes up most stars in the galaxy. So there you go. Fun fact of the day. Okay, so we're going to have 8 beakers, and you're going to transfer, oh, I also forgot, I didn't draw this in here. You're going to have 2 graduated cylinders. So you're going to have your 2 graduated cylinders. They're going to be full of the brown stuff, which I think is more orange, but whatever it is. And what you're going to do is transfer that into beaker number 1. These are going to be labeled on the beaker. Okay, and then you're going to also transfer the stuff that's in your second graduated cylinder into beaker number 1. This counts as one transfer because each molecule has moved one time. Okay, then you're going to take everything, the 200 milliliters will be in beaker 1. You're going to transfer it to beaker 2. That will be your second transfer. And then you're going to go to beaker 3, 4, that's an arrow, 5, 6, 7, and 8. You're going to save beaker 8, and you need the mass of it, both before you start transferring stuff and after. And so if we figure out how many transfers we've done here, you just count the arrows, right? So it's 8 transfers, okay? Not because we have 8 beakers, but because we had cylinders and beakers together, right? So that's 8 total transfers. And so what you're going to do is figure out how much material was in the graduated cylinders by subtracting the empty weight from the full weight. Okay, so it's going to be the full cylinder minus the empty. Don't add the weight of the 2 different cylinders together. The 2 different cylinders don't have anything to do with each other. They're just, we're using those to compare uncertainty. So for cylinder number 1 and for cylinder number 2, you're going to do the same thing. Then, once you know how much iron 3 chloride you put into those cylinders, you're going to add those 2 numbers together. You don't add the weight of the glass with it. Okay? And so that's going to be how much your material is starting. And then you're going to do this number 8. It's going to be full minus empty again. And that'll tell you how much iron 3 chloride you have at the end. So to figure out how much transfer loss occurred, you're going to subtract the beginning weight and the end weight. And then to find out how much is lost per transfer, so we're not weighing the mass of beakers 1 through 7. That would take a long time to do it. Instead, we're going to take the total transfer loss and divide it by 8 transfers, because that's how many times we moved it around. And so this will give us an actual number to know how much material gets lost when you go from one container into another. This will be an error that occurs in your future experiments. You can't avoid it sometimes. So it's important to remember it when you're writing your future lab reports, as well as for this experiment too. Okay, so now we have two hypotheses so far. Uncertainty of the graduated cylinders and transfer loss is going to happen. How much is kind of the task to measure in this experiment. Then the next step is going to be to figure out how to clean stuff, because that's another major problem in experiments. If your glassware is not really clean, the contamination can certainly impact your experiments. How do you clean stuff? That's not really a hypothesis, but you know, it's about cleaning anyway. To be a hypothesis, it has to be testable, and how do you clean stuff is not testable, right? There's no quantity with that, so it's really a difficult thing to assess. To make that into a hypothesis, you might say something like, rinsing with water one time will clean the beaker. Okay, it's not a very strong hypothesis, but that's what the sort of thing could be. So I already told you that beaker number 1 is going to be your control, so you're going to have no rinses. Okay, beaker number 2 is going to be the first rinse you do. You're going to do 10 milliliters. You're going to use your small graduated cylinder from your drawer to measure that. So technically, I think that it should actually probably be, I can't remember how many lines are on the graduated cylinders that are small. There's at least 1 decimal place, possibly 2. So you're going to use 10 milliliters of water, and you're going to rinse this. The rinse solution needs to go into a waste container. So in this case, after you've observed what the control looks like, that becomes your waste container. Don't put it in 8. Keep this one clean. We like to recycle this material because you have a lot left over at the end, and as long as it stays orange, we can keep using it. It stays orange as long as you don't put any of your rinses or any of the dropper material into your beakers. Okay, so after you have dumped your rinse into the waste beaker, which is now number 1, you're going to make an observation. Don't forget to put it against some white paper. And then you're going to go 10 mils 2 different times. So 10 mils into here, rinse, dump. 10 more milliliters, rinse, dump. And then you're going to make an observation of what happens, okay? And so you're going to keep doing this until you no longer see any blue. So let's just pretend that I have a negative result here. No blue shows up. In that case, what I'm going to do in beaker 7, I rinsed 3 times to get it clean, right? So what I'm going to do in beaker 7 is I'll rinse with 30 milliliters all at one time. Okay, so that's another hypothesis we're testing, right? So one of them is the answer in my situation. Yours will be different, but the answer in this example would be, oh, it took me 3 times to rinse the beaker clean. And then another hypothesis can compare multiple small rinses with 1 large rinse of the same volume. And so you would want to figure out, what do you think is going to happen? Do you think that they're both going to clean it? Do you think one will clean and the other one won't? And that's the basis for a hypothesis, right? So that's 4 different hypotheses we have. We have one about uncertainty between 2 graduated cylinders. We have one about transfer loss being significant or insignificant, depending what you think. Does it matter? Does it not matter? We have one about how many rinses of small volumes does it take to clean a beaker. And then we have one about comparing multiple small rinses versus 1 large rinse. So you get 4 hypotheses for the price of 1 experiment. Okay, so when you write your introduction, you want to talk about all of these things. You want to define uncertainty. You want to talk about transfer loss. You want to explain the theory behind this experiment. That's what an introduction is for. You also want to include a discussion about the hypotheses. Try to avoid using words like I and we, okay? In science, we write in what is called third-person omniscient voice, which means no person is ever mentioned in scientific papers, okay? Everything is written from a passive voice, so it's already happened, it's past tense, it's already occurred, and it's almost like nature did the experiment all by itself. That's how we write. It's kind of an awkward way to write. So we're going to give you an opportunity to practice that in your introduction, okay? So you're going to make a draft, submit it on Blackboard, and then you get an opportunity to peer review 2 other people's papers. This is a very good chance for you to learn about how you can improve your paper as well. It's just the introduction, that's all you're writing. And in the peer review process, you're going to see an example of a pretty good introduction for this particular experiment. You should not copy anyone else's or the example, but use that as a way to tell what you're supposed to be doing. Okay? And so that's the trace contamination experiment. It's your first experiment in college, and when you're finished, you'll have a waste beaker in beaker number 1. Don't dump that down the sink. We will collect it after you leave lab. And we will have a recycle beaker, beaker number 8. Everything else in between should get cleaned, and you want to leave one of the clean beakers in your drawer and one of the cylinders in your drawer. Okay, so that's the experiment. I'll see you in lab.